All right, I want to look at exercise 91 for Math 5386. This is from chapter 5 on functions, basic concepts. So suppose we have this mapping, this function f from a to b, and also a function g from b to c. And suppose they are bijections. That means they are one-to-one and onto. So what we're supposed to show in part A is that if, well, I don't know why that says if. Show that, I don't need an if there, show that g of f inverse equals f inverse of g inverse. So I want to show that the inverse of the composition, g of f, is the composition of g inverse followed by f inverse. That's what I want to show. The idea for the proof is to take any c in the codomain of this composition, which is C, and show that it's the same if I apply the inverse of g of f to it, or if I apply this f inverse of g inverse of c. Show I get the same thing for any element in C. So first of all, we already know that f and g are bijections. That was what was given to us in the first place. And so by a couple of other exercises in the past, exercise 76 and 87, we know these things are bijections. So with these two exercises, we know that, and it's okay to use that because this is exercise 91. It's after 76 and 87. If G is a bijection and F is a bijection, then G of F, the composition, is a bijection. Also, the inverse of a bijection is a bijection, so G of F inverse is a bijection. Also, F inverse and G inverse are bijections, and their composition, F inverse of G inverse, is a bijection. So all of those are bijections. So let's pick any C in C. And because G of F is a bijection, that means it's one-to-one and onto. So in particular, because it's onto, there is a unique A in the domain of the first function, f, so that g of f of a is equal to this c, because we have a bijection. It's one-to-one and onto. That makes, there is one and it's unique. So since g of f of a equals c, we can use the existence of this inverse of g of f and say the inverse of g of f applied to c is a. Additionally, because g of f of a equals c, then using notation, that means g of f of a is equal to c. And because g is a bijection, because g, where did we get g was a bijection? Way up here. Because g was a bijection, we have a unique b in the domain of g, such that g of b is equal to c. Therefore, we can use this inverse notation. G inverse of C is equal to B, changing the input and the output. So now, by the transitive property of equality, we have G of F of A equals G of B. G of F of A was equal to C, and G of B was equal to C. So since they're both equal to C, G of F of A is equal to G of B. G is also one-to-one. It was a bijection. So if it's one-to-one and G of this input equals G of some other input, that means those two inputs are equal. So F of A is equal to B. F is a bijection, so that means that we can rewrite this statement, F of A equals B, as F inverse of B equals A. And now we can use some substitution. Instead of F inverse of B, I can use the fact that G inverse of C is equal to B. So instead of F inverse of B, I have F inverse of G inverse of C is equal to A. And then combining F inverse of G inverse, I could say that's F inverse composed with G inverse of C. And finally, I'll use that transitive property of equality again f inverse of g inverse of c is equal to a, and also g of f inverse is equal to a. So both of those are equal to a. So that means for any c, for every c in c, g of f inverse of c is equal to f inverse of g inverse of c. And therefore we've proven that g of f inverse is the same as f inverse composed with g inverse. Next, I'd like to look at part B. Part B says, suppose that we have a couple of mappings. F is a function from x to y, and g is a function from y to x. We want to show that g is the inverse of f, if and only if f composed with g is the identity mapping on y, and g composed with f is the identity mapping on x. This is an if and only if proof, so we need to prove two directions. We need to show that if g is the inverse of f, then these two things are true. And we need to show the other direction, if these two things are true, then g is the inverse of f. So I've got two parts of this proof. The first one, I've got this arrow indicating it's pointing to the right, so we're going to suppose that g is the inverse of f. That means, by definition of inverse, that for every x in the domain of f, g of f of x equals x, and that g of f is a mapping from x to x. And therefore, since g of f of x equals x, that's what the identity mapping does. So g of f is the identity mapping on x. Similarly, for every y in y, f of g of y is equal to y, and f of g is a mapping from y to y, and so we have f of g is the identity mapping on y. So that's that direction. Not too difficult, just using the definitions of what it means to be the inverse. The other direction, starting with f of g is the identity mapping on y, and g of f is the same as the identity mapping on x. Let's choose any x in this set x, the domain of f and the range of g. G of f equals the identity of x means that g of f of x equals x, and so in this other notation, g of f of x equals x. And similarly, if we choose any y in this set y, f composed with g is the identity of y. Identity mapping on y means f of g of y equals y. And using this other notation, f of g of y equals y. And so if we look back at the definition of inverse, we get that g of f of x equals x and f of g of y equals y for all x in x and all y in the set y. That it means that f and g are inverses of each other. So that's that proof. Finally, last proof says that if f mapping x to y is a bijection, show that the inverse of show the inverse of f inverse is f. So another way to say that is the inverse of f inverse is the same as the mapping of f. We know at the beginning that f is a bijection. We were given that. So by proposition 85, it said every bijection has an inverse. So f does have an inverse, and it's called f inverse. And by exercise 87a, f inverse is a bijection. The inverse of a bijection is also a bijection. And since f inverse is a bijection, by that same proposition, f inverse has an inverse, and I'll call it f inverse inverse. We're trying to show that f inverse inverse is equal to f. So let's pick any x in this domain of f, set x. Then there is a y in the set y such that f of x equals y, because f is a function, And because f has an inverse, f inverse of y is equal to x. Because f inverse of y equals x, then f inverse inverse of x equals y. Using substitution, notice that we have f of x equals y and f inverse inverse of x equals y. So f inverse inverse of x equals f of x for every x in x. So since those are the same for every x in x, that function f inverse inverse is the same as the function f. That is to say, the inverse of f inverse is f.